We have talked quite a bit about interpolation and a few different ways to do it. For evenly spaced data points, we have seen that Gregory Newton and Lagrange give us the same result. Based on trends we saw with second and third order interpolating polynomials, we could be led to believe that higher order interpolating polynomials will give us even better approximations to the true value. Brace yourself, that illusion is about to be shattered. Here we see what is known as Runge's function. It appears fairly smooth and well behaved. This should be easy to interpolate, right? Starting with a second order interpolating polynomial, we see room for improvement. What happens if we increase the order? Will that give us a better fit to the data? This fourth order looks a little more bell-shaped than the second order, but notice that it's dipping below the x-axis between 2 and 3. That certainly doesn't match the data of Runge's function. It's getting even worse for a sixth order interpolating polynomial. Yes, it's true that the approximation passes exactly through the data points we supply. However, in between those values, the polynomial deviates from the smooth curve we saw first. Excel will only fit data up to a sixth order polynomial, so that's where I stopped. If you care to employ what we learned in the second lesson on Lagrange interpolation, try fitting an 8th or even 10th order polynomial to the data. Trust me, the oscillations between data points become even more wild. We won't delve too deeply into why this happens, but let me reassure you that there are ways we can mitigate this effect. One is to sample our data more toward the ends than the middle. This uneven spacing is taken at Chebyshev nodes. That's all the more I'll say about this approach for now. Just be aware that it does exist. The method I want to focus on for now is breaking the function into a bunch of smaller segments. Here we see Runge's function divided into 6 equally spaced segments, as denoted by different colors. This is a data table for Runge's function. It's the same data I used for the sixth order interpolation polynomial earlier on, and we are going to use it in a different way here shortly. Take a look at this 7 by 7 matrix. Remember that I split Runge's function into 6 segments. The fact that 6 plus 1 equals 7 is not a coincidence in this case. The d's are unknowns. That's what we're going to solve for. The y's are known. We plug these values in from our data table. Don't worry where all this stuff comes from just yet. We can explore that in another lesson. For now, just focus on how to use it to find our interpolating polynomials. As just mentioned, we plug the data from our table into the vector on the right-hand side of the equals sign. Here I have just simplified what we saw on the previous screen. Symbolically, I show here that our unknown vector of d's can be solved for by multiplying the inverse of the 7 by 7 matrix and the y vector. In reality, there are better ways of doing this than directly taking the inverse, especially since we have a tri-diagonal matrix. That means the only non-zero entries appear on the main diagonal, one above and one below. Every other entry is 0. I will say no more about that for now. On the very right, I have given the values of d. We will get 6 different cubics, one for each segment we split Runge's function into. Those can be calculated according to this prescription. Once again, don't worry where this comes from just yet. Focus on how to use it for the time being. Let's look specifically at f sub 0. Now the subscripted i's have become numbers. Here I plug in the numerical values for each variable. Y's come from our data table. D's come from our matrix solution. The polynomial at the bottom is our answer. We can do the same thing for every other segment. The results are summarized here. Then we can graph each segment one by one. That is shown in color coordination here. Notice that it looks very similar to the original Runge function we wanted to interpolate. There are no wild oscillations between data points. Note quickly that each cubic is a function of t. and t ranges from 0 to 1 in each case. So we don't use the x values at all to plug into our cubic. The data fit so close that a picture comparing the two graphs would be hard to visually distinguish. As such, I present this table of data instead. I compare the spline approximation to the true value of Runge's function for each x. The absolute error is simply the difference between the two. Notice in colored boxes that the error at each data point we input is equal to 0. This is because the interpolating spline passes exactly through those points. Looking at the column for absolute error, I see only 4 times on each side that our error exceeded 1 over 100. This is a lot better than what we saw at the beginning of the lesson. However, if we are still unsatisfied with these results, what could we do to make them better? If you said chop the function into more segments, I heartily agree with that. We have seen consistently throughout our studies of numerical methods that decreasing the spacing between data points tends to result in increased accuracy. Today, we have found a cubic spline interpolation for a given set of data. In the next lesson, we are going to see where the matrix equation comes from and how this beautiful technique blossoms from a handful of simple constraints. Stick around for that.